Have you ever stopped to wonder what gives a molecule its specific shape? You know, why is water bent, but carbon dioxide is a perfectly straight line? Well, it's not random, and it's definitely not magic. It's all about architecture. Every single molecule has a blueprint, a precise set of rules and measurements that define everything about it. And today, we're going to unpack that blueprint.
So what's actually in this molecular blueprint? It's way more than just a list of atoms, right? I mean, saying water is 2 hydrogens and 1 oxygen doesn't tell the whole story. The real identity comes from the specs, the exact distances between those atoms, the angles they're locked into, and just how strong those connections are. These are called bond parameters, and they're basically the laws of physics that govern the entire molecular world.
So here's our plan for exploring this blueprint. We're going to start with the basic dimensions, then look at the angles that give a molecule its shape. We'll check out the structural integrity of the bonds, see what different kinds of connections look like, and finally put it all together to see how this master plan really works. Okay, first things first. On any blueprint, you start with the dimensions. And in the world of molecules, the most basic measurement we've got is the distance between two atoms that are stuck together. We call this bond length, and it's our ground zero for understanding molecular structure. Now, that key phrase is equilibrium distance. See, atoms in a bond aren't just sitting there frozen. They're constantly vibrating, moving a little closer, a little farther apart. The bond length is that perfect sweet spot, the average, most stable distance between their centers, or their nuclei. It's a point of perfect balance. And chemists can actually measure this stuff with incredible precision using some pretty cool tech like spectroscopy and X-ray diffraction. This image really helps us see what's going on. Look at the top part. The bond length, that big R, is just the covalent radius of the first atom, Ra, plus the covalent radius of the second atom, Rb. Simple as that. Now, check out the chlorine molecule down below. The covalent radius, that 99 picometers, is half the distance between the two chlorines that are bonded together. Think of it like a tight handshake. But see that much bigger circle? That's the van der Waals radius. That represents the atom's personal space, how close it can get to a different, non-bonded molecule before they start bumping into each other. So covalent radius is for a handshake, van der Waals radius is for respecting personal space. And here's some real-world data. A hydrogen-hydrogen bond is super short, just 74 picometers. A chlorine-chlorine bond? Much longer, at 199, because chlorine atoms are just plain bigger. And take a look at the oxygen and nitrogen bonds. Their lengths are different for a really interesting reason, which we'll get to in just a minute. These numbers are the hard facts of our molecular blueprint. All right, so distances are one thing, but molecules aren't just one-dimensional lines, are they? To build an actual 3D shape, you need angles. The bond angle is basically the protractor in our molecular toolkit, and it's what defines the geometry of the whole structure. I know, that definition sounds pretty technical, but the idea behind it is actually pretty simple. The electrons that make up the bonds hang out in these special zones called orbitals. And since all those electrons are negatively charged, they naturally push each other away. They try to get as far apart as possible. The final arrangement they settle into is what sets the angles between the bonds. And the most famous example of all, water, the angle between the two hydrogen atoms with oxygen in the middle is a very specific 104.5 degrees. It's this one number, this one angle, that's responsible for water's iconic bent shape. And that shape is the reason for almost all of water's amazing properties, from why it's such a great solvent to why ice floats. It's all because of that angle. Okay, so we've got distances and we've got angles. Our blueprint is starting to look like something. But how sturdy is this construction? Is it built to last? To figure that out, we need to measure the energy it takes to actually break a bond. This measurement is called bond enthalpy, and it's basically the structural integrity test for our molecule. Put simply, bond enthalpy is just a measure of how strong a bond is. The unit is kilojoules per mole. A mole is just a giant number of molecules. Think billions and billions and billions. So this tells us how much energy it takes to break a huge number of these bonds. But all you really need to remember is this. The bigger the bond enthalpy number, the more energy it takes to break it, and the stronger and more stable that bond is.
Now, here's where things get a little nuanced. For a simple molecule like hydrogen gas, H2, there's only one bond to break, and it always takes exactly 435.8 kilojoules per mole. Easy. But in a more complicated molecule, like water, which has 2 OH bonds, things get weird. Breaking the first OH bond takes 502 kilojoules. But after that one's gone, the whole chemical environment changes, and breaking the second OH bond only takes 427 kilojoules.
So how do scientists talk about the strength of an OH bond in general? Well, they just take an average. It's that simple. We add the energy for the first break, 502, to the energy for the second one, 427, and then we just divide by 2. And that gives us the average bond enthalpy of 464.5 kilojoules per mole. That's the standard number you'll find in a chemistry textbook for an OH bond. All right, next up, let's think about the hardware holding our blueprint together. Are the atoms connected by 1 screw, 2 screws, maybe even 3? This idea is captured by a really simple but powerful concept called bond order. This one is beautifully straightforward. When you draw out a molecule, bond order is literally just the number of lines you draw between 2 atoms. It's a count of the number of electron pairs being shared between them. That's it. And these examples show it perfectly. In a hydrogen molecule, H2, the atoms share 1 pair of electrons, so its bond order is 1. We call that a single bond. In an oxygen molecule, O2, they share 2 pairs. Bond order is 2, a double bond. And in nitrogen, N2, they're sharing 3 pairs, giving it a bond order of 3, a triple bond. See? Simple as 1, 2, 3. Okay, so we've got our key players: bond length, bond angle, bond enthalpy, and bond order. But these aren't just a random list of numbers. They are all deeply connected to each other. And once you understand the relationship, it's like you've discovered the master plan behind all of molecular design. And there it is. This one sentence is the master key to everything we've been talking about. It's the central rule of our molecular blueprint. So let's break down exactly what that means. Here's the deal in plain English. As you increase the bond order, so as you go from a single to a double to a triple bond, 2 things always happen. 1, the atoms get pulled in tighter, so the bond length gets shorter. And 2, the bond gets way, way stronger, so the bond enthalpy goes up. It's just like using more screws to hold 2 pieces of wood together. The connection gets tighter, and it gets a whole lot harder to pull apart. And you don't have to take my word for it. Just look at the data for carbon-carbon bonds. A single CC bond is 154 picometers long. A double bond yanks those carbons closer, down to 133 picometers. And a triple bond, they're pulled in super tight, at just 120 picometers. This is the hard evidence that proves the rule. More bonds mean a shorter, stronger connection. Every time. See, these parameters aren't just for describing molecules that already exist. They give us incredible predictive power. By understanding these basic rules of length, angle, strength, and order, chemists can actually design and build totally new molecules with specific properties. So the question I want to leave you with is this. Now that you know the rules of the blueprint, if you had the atomic building blocks, what would you create?